In this video, I'd like to talk more about geometric series by looking at a slightly more complicated infinite geometric series. And when we know that these are geometric, we essentially just need to find the common ratio. And remember, for a geometric sequence or a series, to find that common ratio, we're essentially just looking for the number that we multiply by to go from one term to the next. And the way to find that, you can always take one term, whichever term you want, and then divide it by the term before it. So let's find that. We can take 8 over 25, and we're going to divide that by 4/5. And since we're dividing by a fraction, it's the same thing as multiplying by that fraction flipped over. So multiplying by 5/4, the reciprocal of this fraction. And when we carry out this multiplication, we would get 40 up top, and 25 times 4 makes 100. And 40 over 100 simplifies to 4/10 or 2/5. So it looks like our common ratio is 2/5. We can check this. Since 5 multiplied by 2/5, the 5's cancel, and you get 2, which is what you'd expect. And 2 times 2/5 would be 4/5. So this does make sense. And the reason we want to find the common ratio is that to actually add this up, we want to use a little bit of a trick involving that common ratio. So let's first call this sum S. So we use S for sum since we're adding. And what we'll do is take this infinite geometric sum and we're going to multiply it, the entire thing, by whatever the common ratio is. So in this case, 2/5. So we have 2/5 multiplied by S. And let's just go term by term. We are just distributing the 2/5 to every term in the series. And 5 times 2/5 is just 2. 2 times 2/5 is 4/5. And 4/5 times 2/5 would be 8 over 25. And 8 over 25 times 2/5 would be 16 over 125. And of course, you could keep going. 16 over 125 multiplied by 2/5 would be 32 over 625. And of course, it's infinite. It's going to go on forever. And the reason we do this is so that now we can take this top infinite geometric series and subtract this bottom one, this green one here that we just created. So we can say that our first infinite sum here minus this new one we created, 2/5, this is a solvable problem. And basically, we just want to notice a pattern. So we're taking this infinite sum up top and subtracting this infinite sum down below. And notice for this top sum that it has this term of 5. But there is no 5 from this bottom sum to subtract out. So when we take their difference, when we subtract here, we would have 5 left over. And then we just go term by term. Since notice, we have 2 here, and we're subtracting this 2, so those cancel. We have 4/5 minus 4/5, those will cancel. 8/25 minus 8/25, that's also 0. And so on. 16 over 125 minus 16 over 125, they will cancel. And every term in each of these series after that will also cancel, since you have the same terms up here as you do down here. So they're all going to cancel out, and the only thing we're left with is this 5. And we have this equation now involving S, which we can solve for. That's our missing variable. And if you have something and you take away 2/5 of that something, you would have 3/5 left over. So S minus 2/5 of S would be 3/5 of S, and this is equal to 5. And we can solve this, multiply each side by 5. So we get 3S is 25. And divide by 3, we get S is 25 over 3, which is 8 1/3, or 8.3 repeating if you want it as a decimal. So we were able to add up this infinite sum. Like I mentioned, this is just 8.3 repeating. But like I mentioned in the last video, The only way this is possible to actually get some finite answer for these geometric series is that our common ratio has to be less than 1. Now, it can also be, if I call this r, it can also be bigger than -1. So it can be a negative fraction, and that's something we're going to look at in the next video.